Last class was a while ago. We learned about solution stoichiometry. Solution stoichiometry is critical for the stuff that we're doing this week as well as next week, which is titrations. Unfortunately, we stopped just short of titrations. We'll be talking about that today. So in solution stoichiometry, it's stoichiometry. We're converting from one chemical to another. In our example here, we need a balanced chemical equation that relates nitric acid, HNO3, and barium hydroxide, BaOH2, which we haven't learned about how to make those yet. And so I just gave you that. We need that to do the stoichiometry step. The rest of the stoichiometry step is actually that's stuff that we've done before. It's nothing new. It's just that we're doing it with solutions now. And so we're going to be dealing with volumes, like milliliters, and we're also going to be dealing with molarity. Molarity is like our new molar mass. It's our grams per mole, but instead of grams per mole, it's moles over liters. And I talked about how we're not going to be using this M1V1 equals M2V2 because that's only for diluting solutions. So you can watch the end of last lecture if you'd like a review on what we did for solution stoichiometry. So acid-base titrations is what we're doing this week. We're a little behind, so that's why we haven't talked about it yet. But solution stoichiometry is useful in a lab procedure that we call a titration. In a titration, a substance in a solution of known concentration, so we have the molarity of this concentration, reacts with another substance in a solution of unknown concentration. So we can find the molarity of that unknown concentration. It's also important that we know what the chemicals are so that we can do a balanced chemical equation and know how they react. When we react an acid and a base, the net ionic equation, that is only things that react, removing our spectator ions, for an acid, hydrochloric acid, for a base, sodium hydroxide, this is our net ionic equation. H+, that's the active part of the acid, reacts with OH-, that's the active part from a base or produced from a base, react to form water. So this is the reaction that we are doing in every acid-base titration. For all of them, every single one, that's the reaction that we're doing. So 1H+ reacts with 1 OH-, and it produces 1H2O. For example, let's say that we've got a hydrochloric acid HCl solution represented by this molecular diagram. We're removing the Cl parts. These are just H+. So we've got some H+ floating around in solution. That's representing our acid. What we do in an acid-base titration is we would put our acid down here in the Erlenmeyer flask. And we've got 3 different steps. So we're looking at when we start here in the first one, then this middle one is partway through, and then the last one is when we're done with the titration. So we've got our acid in the flask down below, and we've got our base in a burette. And a burette is just a tool for measuring the amount of substance that we titrate or that we add from the burette. So it's got this thing here that I'm circling that's called a stopcock. And so that lets you either open it to let solution flow out of the burette or close it so that solution stops flowing out of the burette. And you can do it drop by drop, or you can do it in big bursts. You can just let it run. And we'll talk about that more in lab. I'll show you how to use those. And so we would have a solution of base in our burette. We know how much we loaded into the burette, and it's got these volume markings that you may be able to see, so 40 or 20, 30, 40, 50. And it counts up as it goes down because that's measuring out how much we added. So it measures how much is added. A common mistake that I see with these burettes, they're set up to be easy for you to read, easy for you to measure out, figure out how much solution you've added. Common mistake that people will do is they'll take the number that's here and subtract 50 from it, or do 50 minus the number that's here. It's just whatever the number is that's written down, that's the measurement. There's no subtract 50, there's no add 50, nothing like that. Okay, so we've got our base in the burette. We open up the stopcock and we let some of the hydroxide in. The hydroxide and the H+, the base and the acid, react in the flask and form H2O. So we've got a couple H2Os in there. And then we add some more, and there's this indicator, a color-changing dye, that we add to our solution that will turn pink once we've used up all of our acid in the flask. So it turns pink when acid is used up. And what that lets us know is that we've got no more acid, and so the amount of base that we added is the same as the amount of acid that was in the solution. So all the H pluses have reacted with all the OH minuses, and that's what we call our equivalence point. And I think we've got more about that here. So the equivalence point is when the H plus and the OH minus in the flask are equal, and used up. They neutralize each other. And that's often signaled by an indicator. The indicator that we're going to use is phenolphthalein. You don't need to know how to spell it, which is probably a relief to many of you. That's how you spell it, phenolphthalein. And it turns fuchsia. You also don't need to know how to spell fuchsia, which may also be a relief to many of you. So when we have, in our case, I think we're going to have acid in the flask. When we have got acid in the flask, the phenolphthalein is going to be clear. And when we reach our equivalence point, it's going to turn pink or fuchsia. I will show you what that looks like in the lab. Typically, when we're doing a titration, we are going to know the concentration of one of our solutions, and we will not know it for one of them as well. So oftentimes, we'll know what's in our burette. We'll know the concentration of what's in our burette, and we'll have to do a titration to figure out the concentration of what's in our burette, which we'll be doing today. So it's kind of a two-parter for a lab. And if we carefully measure the volume of each solution, we can use solution stoichiometry to figure out the concentration of the unknown. All right, so an example of this is coming up. So we're going to be adding sodium hydroxide in a liquid to an HCl solution. The sodium hydroxide, in our case, will be known. The HCl solution will have an unknown concentration. When they reach stoichiometric proportions, aka the equivalence point, that's when our solution will change colors. And when we do this with phenolphthalein, usually we're just adding a small amount. It's a very strong dye, so we'll be adding a couple of drops of, like, I think it's 0.1% solution, so not very much at all. And our goal is to get a very light pink endpoint. The lighter the pink endpoint, assuming it's a permanent color change, the lighter it is, that means that we haven't reacted all of our dye, so we're really good, we're really secure in our endpoint. We know that we're right at or about at the equivalence point. If you overshoot it, you'll get this dark pink color, and you'll get this dark pink color if you overshoot it by 1 drop or 10 milliliters or 50 milliliters or 100 milliliters. Once it turns this dark pink color, that's as pink as it's going to get, and we don't have any sense of, are we over by a little bit or are we over by a lot? So this isn't always bad to get this dark pink endpoint. If you know that you added 1 drop or 2 drops or 3 drops and it went from clear to that dark pink endpoint, we could be kind of still really good in terms of the amount that we added. We know that we've got a good equivalence point. But if you just let it rip for 40 milliliters and then it was this dark pink color, we have no clue if we're over by a little bit or if we're over by a lot. So that's why we shoot for this light pink endpoint, because it lets us know for sure that we've got a good equivalence point or we're really close to our equivalence point. Questions about any of that? There's a certain amount of luck in getting that light pink endpoint. Okay, so here's what calculation for an acid-base titration might look like. In this case, we've got calcium hydroxide. So we are trying to find a mass of calcium hydroxide present in a sample if it is titrated to its equivalence point. Equivalence point here just lets us use our solution stoichiometry. That's all that it is. It's just signaling to us, yes, we can do stoichiometry, we can use our ratio from our balanced equation. That's all that equivalence point is signaling to us in this case. And it's taken to its equivalence point with a certain number of milliliters of a known concentration of HNO3. And we've got a balanced equation. So the place to start is with the stuff that we know. That's going to be our 44.02 milliliters and our 0.0885 molar HNO3. So it'll be helpful to convert our milliliters into liters, so we divide by 1,000. And then it may also be helpful to remember that molarity is moles over liters, so we can switch those units out for free. So we are trying to find grams calcium hydroxide. To get to grams of calcium hydroxide, any ideas on what we need? How can we get grams of something? Moles. We need moles. So we can get to grams of calcium hydroxide from moles of calcium hydroxide using what? It's not molarity. Molarity is moles and liters. Molar mass, because molar mass has grams and moles. And we can calculate a molar mass for calcium hydroxide. We'll do that in a bit. In order to get to moles of calcium hydroxide, what could we use to get there? do we have a molarity for calcium hydroxide? We don't. We can do stoichiometry, aka ratio. So if we can get to moles of HNO3, then we can get to moles of calcium hydroxide. Because the problem says that we're at the equivalence point, that means that we can use the stoichiometry in our balanced chemical equation. So we're going to start with the liters and the molarity. We'll find moles of nitric acid. So starting with liters of HNO3 and using our molarity, we'll get to moles of nitric acid. And then we can do a stoichiometry step since we're at the equivalence point. That'll get us the moles of the thing we want. And in this problem, we're going to figure out the grams of the calcium hydroxide. We don't have a volume given or anything like that. Other times, instead of this last step using molar mass, we might have a volume of our calcium hydroxide solution, and so we'd be able to calculate a molarity for that. I could show you what that looks like. We can just make some numbers up. Any questions about the solution map setup? I started working from the endpoint towards the beginning because I feel like that's sometimes helpful for students figuring out, like, hey, where do we need to get to the answer? We can work backwards, and sometimes that'll give us a better solution map. Okay, so our 0.04402 liters. How do we use liters with molarity to get moles? Do we multiply or divide? If we use our little triangle thing, or a pyramid thing, for any pyramid enjoyers out there. So a bad pyramid looks more like a volcano. But if we're finding moles, we multiply molarity and liters. So we'll multiply by our 0.0885 molar. The other thing that we can do is swap out, instead of molarity, if we write it as moles over liters, then that lets us look at the units. We've got liters to start with. Liters is in the bottom for our molarity. So we'll get those to cancel out if we multiply, and then we'll be left with moles. That's the way that I like doing it. So if we do that, then this will be the number of moles of nitric acid that we have, or that we add. So let's just see what that number looks like. So that number is going to be 0.00389 ... moles HNO3. So this is the amount that we would have added from our burette into our little flask. And when we do that, it reacts with calcium hydroxide. Our ratio is that we used 2 HNO3 for every 1 CaOH2. So we can figure out the number of calcium hydroxides that we had, or the moles of calcium hydroxides that we had, using our stoichiometry step. That's what we're doing here in blue. 0.0019 dot 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 moles calcium hydroxide. And then our last step is to take our moles of calcium hydroxide and turn it into grams of calcium hydroxide. We've got 1 calcium, 40.08 grams per mole. The oxygens are each 15.999. The hydrogens are each 1.008. So a total molar mass of 74.094 G over MOL. So multiplying our moles by our molar mass, we'll get our moles to cancel. We'll be left with grams. And there were 0.144 grams of calcium hydroxide in that solution, apparently. Questions about any of those steps? Hopefully getting our brains back into chemistry mode after a nice Easter break, spring break. If we instead wanted to find molarity So if we switch the problem up a little bit, let's say that we had 25.15 milliliters of calcium hydroxide solution. And we wanted to find molarity of calcium hydroxide. So all that's going to change for this problem is once we get to this moles of calcium hydroxide, instead of using our molar mass, we use our milliliters converted to liters to find molarity. So this last step here is going to change. We would take our 0.0019 moles of calcium hydroxide, and we're trying to get to molarity. Molarity, remember, moles over liters, so we need to divide the moles that we have here by the liters of the solution. So 0.02515 liters, converting that milliliters to liters. So that molarity would be 0.0775 molar for its concentration. And that's more like what we'll be doing in the lab, figuring out molarity rather than grams. All right, any questions before I turn you loose on your own problem to try? Okay, what mass of oxalic acid, having this formula H2C2O4, is present in a sample that is titrated to its equivalence point with 18.09 milliliters of this concentration of sodium hydroxide? The balanced chemical reaction is given to you there. So I'll give you a couple minutes, give that a shot, and then we'll go through it together. All right, so sorting some of our information. We were given two numbers that go with sodium hydroxide. These numbers go together, meaning that they're paired, they're matched, they're for the same chemical. And we are asked to find mass of oxalic acid, and we're given a chemical formula for that, conveniently. Since we're being asked to find mass, I think it's reasonable that we see a chemical formula and mass, and we come up with a molar mass. So 2 times 1.008 plus 2 times 0.11, and 4 oxygens. Oxalic acid has a molar mass of 90.034 grams per mole. We're also told that we're at the equivalence point, or it's titrated to the equivalence point, which just means that we can use this balanced chemical reaction. We know the stoichiometry, we can do the ratio stuff. I am going to start with this, with clicking the wrong button 15 times. I'm going to start with these two numbers that go together, the milliliters and the molarity. I like to start with volume because it's just 1 unit. And molarity is secretly 2 units. It's moles over liters. You can start with either of them. It doesn't really make a difference. So we've got that many liters of sodium hydroxide. If we multiply that by our molarity, 0.2235 moles per liter, then we get moles of sodium hydroxide left over. That's our units that remain. And we know that our sodium hydroxide reacts with our oxalic acid, and we've got that ratio in our balanced chemical equation. So we can add in another step, do our stoichiometry step. We have sodium hydroxide, so the 2 NaOH is going to go down here on the bottom. So we put in 2 NaOH, and that reacted with 1 oxalic acid, H2C2O4. So our sodium hydroxides cancel, and this tells us the number of moles of oxalic acid, H2C2O4, that we have. And then our last step, since this is the same as the previous problem, we're going to use this grams per mole to get rid of our moles and turn into grams. So 90.034 grams per mole. Plug that all into our calculator. And we get 0.1820 grams of oxalic acid. I wrote it C2H2O4 because that's the way Google would normally tell you. That's like the normal ordering. It's just an oopsie on my part. It's the same thing. Questions about doing those steps? Okay. Other stuff that we can do that's related to aqueous solutions. You know and love or fear and hate molarity. There's a unit that I like less than molarity. I actually kind of like molarity. There's another unit that's similar. You may remember 2 weeks ago I mentioned that molarity is capital M, and it has to be capital M because lowercase m is something else. We're going to learn the lowercase m here pretty soon. So there are some properties called colligative properties, which basically just means like sticking together properties. And colligative properties depend on the number of dissolved solute particles. Just on the number. It doesn't matter what type of solute particles, only how many there are. And a couple of our colligative properties are freezing point depression and boiling point elevation. These are things that we take advantage of in our cars, in your antifreeze, to keep your engine from overheating. So what happens is you add a non-volatile solute, so a salt, or some like dense liquid, to another liquid, and that increases the temperature range. Extends or widens the temperature range. So the freezing point drops and the boiling point elevates or goes up. It's like we might have normal freeze and boil. So our normal, and if we add that non-volatile liquid or non-volatile solute, we've got a bigger range where our liquid is a liquid because our boiling point has gone up and our freezing point has gone down. Both of these things happen at the same time. An example of this is if you add salt to ice, that lowers the melting point. So if you've ever done the sort of fun experiment where you take like rock salt and water or like and ice and you like put that in a bag and then you put like heavy cream in another bag and you add those bags together, then you shake them up and you make ice cream. Or just if you make ice cream at home, chances are that you've added salt to it, and that's to lower the freezing point or the melting point of the ice so you can get colder, so that you can make the ice cream. We take advantage of this by adding ethylene glycol to water. That raises the boiling point and lowers the freezing point of the water. The mixture has better properties than the water itself or the ethylene glycol itself. So if you ever buy antifreeze, you can buy antifreeze like just the ethylene glycol or propylene glycol part. You have to mix it with water. You can also buy it pre-mixed. You're buying water, but it's pre-mixed, so that's kind of convenient. You can just put it straight into your radiator. So here's the lower M that I was talking about 2 weeks ago and just moments ago. So for freezing point depression and boiling point elevation are colligative properties. The concentration is usually expressed in molality, which is lowercase m. And molality has the equation of moles solute over kilograms solvent. So this is different in a couple of ways from molarity. So it's a mass unit, and it's solvent rather than solution. In molarity, it's liters instead of kilograms, and it's solution instead of solvent. So we're not including our solute here, it's just the amount of solvent that we have. So sometimes this is nice, oftentimes it's not nice. And I'll show you, I think on this next slide, I'll demonstrate for you why I don't like molality. All right, we want to calculate molality, lowercase m, of a fructose solution containing 50.4 grams of fructose and 0.332 kilograms of water. Molality, lowercase m, is moles solute, the solid or the minority component, over kilograms solvent, the liquid or majority component. Which of these two chemicals, water or fructose, is our solute? Fructose is our solute. And what does that make water? Solvent. So conveniently, we already have our water, our solvent, in kilograms. That's what we need for our molality. So that'll just plug straight in. However, for our solute, we have grams and we need to turn that into moles. And so we get to do a conversion. So we're going to use our molar mass of fructose. Pull that up real quick. It's 180.156. So divide by that so that grams and moles cancel. And that'll give us our moles of sugar, fructose. .279 meaning there's other stuff behind it. Moles of our solute, C6H12O6. And that goes in the moles solute part. So our molality is 0.279 ... moles over 0.332 kilograms of water we get a value of 0.843 lowercase m C6H12O6. And you might be thinking to yourself, that's not so bad. Anyone thinking that to yourself? That's not so bad. Mr. K, why do you hate molality? If this was capital M, in an alternate universe, how would we pronounce that capital M? 0.843 what fructose? We'd pronounce it molar, just dropping the itty part, right? And if we have molality, and we drop the ity part, then that means that this is a 0.843 mole fructose solution. And I just hate the way that that feels and sounds. It just feels very mush mouth. So 0.843 mole fructose. And that's why I don't like molality. It's a silly reason, but that's the truth. Okay, questions about molality? We use molality for a very limited number of circumstances, so you can be happy about that. One of those circumstances that we use it for is freezing point depression, which is not just being sad when it's cold outside, although that's common. So freezing point depression, freezing point is freezing point, and depression like lowering. So the freezing point goes down. So our flower power goes down. And our freezing point depression equation is given to us here. Our change in temperature, delta T, the sub F for freezing, the change in temperature is equal to the molality times our K sub F. The sub F the little f there being for freezing, and the big K meaning that it's a constant. So you would be given oftentimes Kf, you can find molality, and then you can use that to then find the change in temperature of the freezing point. Different solvents have different values of Kf. These will be given on an exam. It's not something that you would memorize. It would be given to you as a constant. On homework, it might be something that you look up in a table in the book. In the real world, you would just Google it. Any questions about freezing point depression? All right, let's see it in action. Calculate the freezing point of an aqueous 1.42 mole sucrose solution. And for water, our Kf is this nasty looking thing. What is all of this mess? Degrees Celsius, kilogram solvent over moles solute. What's moles solute over kilogram solvent? Yeah, this whole bit, that's just molality, but on the bottom. So really the units here are degrees Celsius per mole, which is lovely. And I have a phone call I need to take. Okay, so calculating freezing point depression, we want to find the freezing point of an aqueous 1.42 molal sucrose solution. We have delta T sub F equals lowercase m times K sub F. We've got our molality, we've got our Kf. So we can find our change in freezing point, change in freezing temperature, by doing 1.42 lowercase m times 1.86 degrees Celsius over lowercase m. The molalities cancel out, and we're left with degrees Celsius. 1.42 times 1.86 gives us 2.64 degrees Celsius. Is that our answer? That is not our answer. This is I don't think it's especially tricky, but this is typically where people mess up with these calculations. They will calculate the change in freezing point or the change in boiling point, and then they don't do anything with that number. They just say, well, that must be my answer. However, that is not our answer. This is the amount that our freezing point will be depressed by, or will go down by. So freezing point drops by 2.64 degrees Celsius. What is our normal freezing point for water? Normally, it's 0 degrees Celsius. And if it's going to drop, that means we're subtracting this 2.64 degrees Celsius. And so our new freezing point, negative 2.64 degrees Celsius. So that's our new freezing point, and that is the correct answer. So the thing to remember for colligative properties questions, there will be some on our exam 4, there's likely to be one on the final as well, is to remember to do something with that delta TF or that delta TB that we'll learn about soon. Questions about that? Okay, if you've never experienced deja vu, coming up soon. The boiling point of a solution that has a non-volatile solute in it is higher than the boiling point of the pure solvent, which is convenient in cars, so we'll use antifreeze. This helps engine blocks in cold climates. It prevents the coolant from freezing, because if it's just water and then it gets below 0 degrees Celsius, your engine block can't circulate frozen water. So it drops the freezing point. We don't have to deal with that particularly much here. But it also prevents the boiling of engine coolant in hot climates, especially since you're generating a lot of heat driving a vehicle, which is something that we do have to deal with here. Okay, deja vu. It's time. This looks awfully familiar. So this is for boiling point elevation. So elevation meaning going up or goes up. So our boiling point is going up, our freezing point goes down. Our boiling point elevation of a solution equation is almost identical to our freezing point, 1. All that's changed is where we had little f's here, we got little b's now instead for boiling. So it's a different constant. It's kb now instead of kf, but otherwise the formula is basically the same. So super simple math-wise, it's just you have to remember to do the adding, the subtracting. And again, these kb values will be given to you. Okay, so let's look at what we might do with this information. So this is a different type of problem because I thought it would be silly to just make you do the same thing again. What is the concentration in molality of an aqueous sodium chloride solution with a boiling point of 101.78 degrees Celsius for water? Our Kb is given. Again, it's helpful to remember that this is secretly delta C, degrees Celsius over m. So we're trying to find concentration starting with boiling point. Just as a reminder, our equation is delta TB, not tuberculosis, m times Kb. Who's got an idea of where to start here? Yes.
If we're trying to find molality, would we have to rearrange the equation?
Yeah, we can rearrange our equation. So we're trying to find this lowercase m. So we can rearrange this, divide both sides by k sub b, and molality equals delta TB over Kb. Do we have Kb? Yes, we were given that. Do we have delta TB? We do not have delta TB. You might think that we have delta TB. We do not have delta TB. We have temperature. Our temperature is 101.78 degrees Celsius. Our delta TB is our change in our boiling point. So how much our boiling point went up how much boiling point increased versus the regular boiling point. And we have the value of our new boiling point. What's our value of our normal boiling point for water? What's regular for water? 100 degrees Celsius. It's normally 100 degrees Celsius, but it's 101.78 degrees Celsius. How much did our boiling point go up? (101.78 degrees Celsius minus our normal boiling point. So our delta TB is 1.78 degrees Celsius. You don't necessarily have to I don't know that the delta TB equation that I wrote at the bottom always works, or if it's going to be flipped sometimes. But it went up by 1.78 degrees Celsius, and so that's our delta TB. Questions so far? All right, so molality equals our delta TB of 1.78 degrees Celsius over our KB that we were given of 0.512 degrees Celsius per molal. The degrees Celsius cancel, the molal pops to the top. So our molality is 3.48 molal sodium chloride. Other colligative properties, colligative related properties include osmosis, which we kind of just talk about, but I don't think I've ever put an osmosis question on an exam. Whether that's good, who knows? So osmosis is a process that you might be familiar with. You may be thinking Jones, not Jones, different osmosis. Osmosis is the flow of solvent, think water, from a less concentrated solution so from low concentration to high concentration. Water moves to dilute concentrated solutions. That's what's happening in osmosis. So if you've got really salty water and not very salty water, the water will flow from the not salty water to the very salty water until they reach the same saltiness or salinity. That's what's happening in osmosis. And this is what an osmosis cell looks like, a container that can do osmosis. So we've got it represented as a beaker with a semi-permeable membrane. The semi-permeable part means that water can pass. But the salt or the other things that are in the solution are not moving. They can't make it through. It's just the salt that can move. So initially, we would start with this situation A. We've got a 0.1 molar solution and a 1 molar solution. And water can pass through this semi-permeable membrane, and it's going to flow from the low concentration solution to the higher concentration solution until such a point that they either reach the same concentration or, because of the pressure of this water being taller, it's tall enough that the pressure is such that it just forces the water through the semi-permeable membrane. That can also happen. If you're wondering why it flows from low concentration to high concentration, you can think of ion dipole forces, even though you probably don't want to. So in this low concentration solution, there's going to be lots of water molecules floating around. They're going to be interacting with some of the salt molecules or other things that are in there. In this high concentration side, there's a lot more of those salt molecules floating around, or sugar molecules or whatever. And so they're going to be interacting more with the water. It's more opportunities for the water to get stuck interacting with these salt or sugar molecules. And so some of the water molecules are going to move from this low concentration solution over, and they'll get stuck. There's all these particles now to interact with, and so they don't end up moving back over to the low concentration side. That's like, if you're wondering why on the small scale, why it does that, that's what I would recommend for you to think about. The other thing, right, osmotic pressure, how tall the column is, it's not really that important. Forget about it. Also shows up in red blood cells. So we've got some pictures of what blood cells normally look like. The reason that it's important or relevant in our lives is for blood cells, but also it shows up when we drink salt water or if you drink ocean water. So you may know that people that get stranded on desert islands out in the middle of the ocean or whatever, right, they have trouble finding water, and so sometimes they'll drink seawater because they're like, oh, I'm so thirsty, I just wish that I could have something to drink. So they drink really salty water. And then that salty water, really salty water, goes through their body and you're full of semi-permeable membranes. And because that solution that's in you now is so salty, it actually pulls water out of your body. And so you actually end up being more dehydrated. You may have heard that you shouldn't drink salt water because it dehydrates you. This is, osmosis is why it dehydrates you. This also happens at a cellular level. So you might know that IVs, fluids that go into your body, are like, they have to be balanced. They're really tightly controlled. And part of the reason for that is because if you put a solution in your body that's isotonic, meaning it's the same concentration, or we can think of it as the same saltiness, then that's fine. Nothing happens. It's the same as the solution that's in your veins. If you put in something that's hypotonic, hypo meaning less than, hypotonic, the surrounding fluid is lower in solute concentration, and that means that water is going to flow into the cells, into your red blood cells. And if that happens too much, your red blood cells pop. Which is bad. There's also the other case where your red blood cells are in a hypertonic solution. So if you put stuff in that's got too much salt in it, the surrounding fluid is more concentrated and water is pulled out of your cells, and then they look evil. They look less evil than the old slides. The old slide looked really evil, which is fun. That's kind of interesting, I think. The other thing, you may have heard about reverse osmosis. I'm probably not going to get tested on this. Reverse osmosis takes advantage of semi-permeable membranes where water can pass through them and this pressure difference. And so what happens in reverse osmosis, rather than letting the water travel to the more concentrated side, you add a bunch of pressure. So you add a bunch of pressure to one side, either by having a really tall column of water or more likely having like big hydraulic press sort of things. And that forces the water through the semi-permeable membrane. And then since only the water can go through the semi-permeable membrane, you're left with nice, clean drinking water, or overly clean, overly sterile drinking water. And then you add salt to it. Questions about any of that? Okay, well, I guess that'll do it then that does it for this chapter, and we'll start acids and bases Thursday.